So I have a Nucleo STM32 F401RE development board, and I wanted to add support for micro SD card, in particular 32 gig drive. So I was kind of looking at what that takes, and hardware-wise, easy. You need to have a socket and a few jumper wires. Software, surprisingly easy. A few clicks, drop in two files, and you're ready to go. I've provided a couple of references here in case you want to dig into it deeper. I'm not going into this stuff, but it's there if you want to see it. So, a socket, I mean, you can buy them for under a buck. If you go to the Far East, if you go to Amazon, they're probably a little more expensive. I didn't really look exactly. This one has 6 connections. It's got power and ground, and make sure you know it's 3.3 volts, so don't apply 5 or you're going to damage stuff. We're going to need a chip select, and that will be an active low signal. And then we have the SPI interface, and in my example, I use SPI2, and that includes clock, master out, slave in, master in, slave out. And I included a pull-up resistor on there. I'm not 100% certain that that's required, but I think it is, because if that chip is not, selected, there's nobody driving that line. So I included a pull-up there. So if we look at the software slash firmware, you go into the IDE. I'm not going to go through all this. I'm just going to quickly outline it here so you know that it's there. Go in there, pick middleware. I'm using FreeRTOS. In particular, make sure you pick it as a re-entrant support, and then you pick the FAT file system. And you get to pick which features you want. There's 4 or 5 of them here in particular. I want to make sure you have. And then under system core, we're going to use serial wire debug, and we change the time base from systick to timer 1 because that's what they want. I'm not sure it's truly necessary, but okay. Continuing on in this, go to system core GPIO, and you're going to have to configure an output to do the SD card's chip select. And I change the label of whatever you pick. In my case, I picked micro SD underscore chip select. And then under connectivity, pick SPI2, or if you want, pick any other of the SPI that's appropriate for you, for your project. In particular, then, for that SPI, configure it for Motorola 8-bit MSB first. Prescaler, you can pick 2, although it really doesn't matter too much what you pick because we're going to be changing the value of this on the fly in the code, so it doesn't matter. These next 2 are pretty critical. Pick low and first edge. And as I indicated on the master in slave out signal, I included the pull-up resistor. At this point, you should be able to just do save and build. You're probably going to get one warning that's down in the FAT file system. It's really a benign warning. We're going to ignore it for now. We'll deal with it in just a bit. At any rate, you should be able to build, but it's still missing the board support package, which we'll talk about here next. So the board support package in this case is going to consist of a single C file and a .h. Now the IDE environment already is going to have these files out there for you, but they're pretty sparse. They're just got the file name, kind of empty functions. And we're going to flesh those out. I'm not going to go through the detail. You can look at the code as well as anybody else, but I'm going to just drop them in and then I'll use them. Those files are located in FAT file system target. And if you change them in the spots where they want you to inside the user code section, everything's maintained. Even if you go back into your IDE, change configuration, and rebuild, you don't have to redo that again. So those 2 files are available out there on GitHub. I got the link right here. And then in the H file, there are 6 defines that I will go through a little bit more detail that you need to set for your project. And at this point, we'll stop and go into the IDE. We'll start by taking a look at what this file system or directory looks like for the project. You have your normal core with your source and include. but under here you'll have FAT for file allocation table based file system, and under there's two folders. There's target down here, and under target here's this user disk io.c and .h. Those are the ones that we modified. And then I'm going to, under middleware, there's third-party FAT file system source, and there's the set of files here. I don't know, 7 or 8 files. I'm going to talk about those because the ones that come with the latest IDE are a little bit out of date, and this will all work even with those files, but I went out and got the latest, and I'll talk about that in just a minute. So if we look at this H file, I tried to document what all this stuff is in here and why you're picking it. So the first one is, do you want to be able to write to the card? I presume so. Maybe you want to do read only. If you do read only, you can set this to 0. I haven't done that. I've left it as writable always. And then you need to provide these two defines, which says what's the SD card's chip select port and pin number, and these are from main.h that the IDE developer created, and that's the micro SD chip select, and then GPIO port and pin. That's pretty straightforward. Here you just put in the name of the SPI that you used. In my case it was SPI2. You can be SPI1, 3, whatever. And then there's two other things here. This is the SPI clock baud rate, slow or fast. I think it goes into CR register 1 if I remember correctly. There's a 3-bit wide field called BR, and that sets the SPI clock based on the peripheral clock that it's using, which in my case I have a 84 megahertz clock, gets divided by 2 to generate the P clock, and if you put in the baud rate setting of 6, I'll get basically 328 kilohertz, and where that comes from I documented it up here. Reference manual 0368 because I'm using the 401, and then section 20.51 describes the SPI control register 1 baud rate settings and what speed you'll get. So if you use this slow baud rate, you get 328 kilohertz. If you use the fast baud rate, you get 10.5 meg. And the reason that we have both of these is that when you initially start to talk to the SD card, the spec says you have to talk to it at a clock speed of 100 kilohertz to 400 kilohertz. So a relatively slow speed. So if you use this baud rate 6, you're going to get 328 kilohertz in that range. Once you've done the initialization and you've talked to the card, you got it in the state where it's supposed to be, then you can switch the clock to a higher number. Frankly, I'm not quite sure how high of a high number we can go. I've played with it. It seems to work perfectly fine, even at a faster rate than this, so I've used 10 at the moment. One reference document that I found particularly useful was this one right here. SD specifications, part 1, physical layer, simplified spec. Even for a simplified spec, it's still 400 plus pages. But this is freely available, and if you're interested in this, I found it very informative. It helped me better understand what this code looked like or how it worked, because recognize that I didn't write this stuff originally. I went out and got it. On the first slide, I put a name in there where I got it from. Matter of fact, his name would be up here in the C file, not in the H file. At any rate, this document was very useful, and everything seems to work fine with one caution. If you're doing a formatting of the drive, the caller to this function provides a working buffer, and in my case that working buffer, I started out with 512 bytes, which is a standard sector size, and everything worked fine. Formatted the card, no issue. But if you look at the way the code works, it says if you give me a bigger buffer, I can format it faster. And the reason it can do that is because instead of writing one block at a time, it can write multiple blocks. So I put in, instead of 512, 1024, and it failed. It got hung up. So I hooked the logic analyzer up, kind of looked at what was going on the SPI bus, and after a point, after just like I think the third block, the memory card says I'm busy and never comes back other than busy, and it stays that way for an indefinite period of time, 3 or 4 seconds at least. So I'm not sure what's going on. I'm not sure if there's something wrong with this particular brand of card that I'm using, or whether it's a more generic problem. Anyway, bottom line is I backed it off from 1024 to 512 and everything seems to work fine. So at this point, we've configured the system, we've updated the board support package in terms of the user disk io.cnh file, and I've updated the main file, which is where I am right now, main.c. And so it does just a couple real simple things. It mounts the drive, assuming that that succeeds. It labels the drive, reads the label back. It tries to read a file content that might have been left over from before. And then after it tries to read that and print out what it found, it would then create that file, and that's it. So if I got a breakpoint set, so we run here, we are at, I've got free real-time operating system running on here. So this is the default task, which is where I put this code. One thing I want to talk about here that I haven't mentioned yet is this board support package has 5 functions that you have to provide, which is providing a link between the FAT file system and the hardware, or underlying hardware. One of those is this disk IO control, and I added a feature to this which allows me to call it with this control debug, and I can turn on or off the request for debug messages to come out through this data console window here. So this function is going to get called. It's going to enable debugging with print K messages, and so that's what this is about. So we come in here, we're going to mount the drive. So I hit, this is a function here, so we call that, and we call the F mount, as you might expect if you're familiar with a normal file system. And the path is just 0:/ here. So that's the name of the drive. There is an option so you can provide letter-based names, but I didn't bother to mess with that. So we'll just hit step over that, and if success, which it is, if it was failed, we would have gotten a message out here. And so we're going to, oh, that's if it wasn't okay. Yep. So we're all good to go here. And we come back out. Results are good. If it failed, we would have done a make file system, which is basically a format. Normally you wouldn't do this. This is only for testing purposes, and if I manually change this result from FROK to a 1, which is a disk error or something, it would format the drive. I'm not going to do that. It takes probably a minute to format the drive. So we're going to set the label. I labeled the drive STM32 F401, and the results were okay. So we're now going to get the label, print out what that label was, and here it came out the debug console, and it says it's labeled that, which is what we just did. We're going to try and open the file, which I think is already on there, and we're going to read what's in that file. We read 13 bytes, I think. Yeah, 13 bytes. And then we'll print that out, and basically it just says hello world, and this is a number as to how many times we've been through that loop. Doesn't really apply the way this code's a bit dated. Anyway, close the file. Then I'm going to reopen that exact same file, but this time for write purposes. I'm going to write that stuff out, and that's it. It's like you got a file system up and running. You can take that little micro SD card out. You can put it in the PC. The PC will see the file that you just wrote. If you format it on this development platform and put it in the PC, it recognizes it. It's all valid. And the flip side is also true. If you format it in the PC, put a file or two on there, put it on the target system, you can see the files. You can add more files to it. You can delete files. So you're pretty well good to go. Now, I'm running with a FreeRTOS, so I have multiple threads and I have reentrancy concerns and multi-thread access concerns both. So one of the things that I require is that you have that's what all this stuff is, all these conditionals. If you don't have the right features turned on, it'll complain. It'll give you an error. So if you're building this and you don't have mutex support so that multiple threads can't come in the file system at the same time, you'll get an error. So that's what this stuff is here, and I just wanted to make you aware of the fact that with this FreeRTOS, you got to be concerned about multi-threaded access. Now, the code that I got this from originally didn't have any of this thread awareness, and they just used fixed timers that burned CPU cycles in order to get the timing that they wanted. I really didn't want that, so I replaced the timers that they had with timers that are real-time operating system aware, OS delay. So they'll basically give up the time so that other threads can run while we're waiting for something to happen down here at this driver level. The original code that I got, nice piece of code, very generic, supports lots of different options, lots of different features, but it was, first off, it was a little dated. It didn't work with this IDE environment anymore because things had changed enough in this code base that it just wasn't compatible anymore. And secondly, it was a little more obtuse and it was too capable. It was just a little hard to understand. So I've stripped this down to be a much simpler design, and maybe design isn't the right word, just implementation, based on what that original code was. And so it's a lot more contained. Really, the changes are now just in that one file and no place else, as opposed to scattered across a number of files that they had in their source. And everything that's in here is done in such a way that if you rebuild the IDE, you don't have to touch any of this stuff again. You're all good to go. Now, that said, I'm going to change one statement here in just a second. So I'm back looking at this FAT file system source, and as I indicated, I don't know, there are 6, 7, 8 files here, and these come automatically with the STM32 Cube IDE environment when you pick FAT file system. They get created and dropped down in here. These files are kind of old. I went back to the original author of this. I don't really know exactly what his name is. CHA and then with a capital N. So I'm assuming it's somebody in the Far East, but I'm not sure about that statement. At any rate, I found his website, which again is on that first slide, and he has all this code out here, including a much more recent version of this code. I went and looked at what that is, and they have a number of fixes since this stuff was originally done that was of interest to me. In particular, some of the multi-threaded operations. It looked like there might have been a couple of holes that they fixed. So I've dropped in the latest code from him, and I think it's version I think it's called R.015 or something like that. Anyway, it's the latest stuff that's out there. I've dropped it in. It really just is a form, fit, and function replacement. Other than the format is a little more capable now than what the original one. The original format, you could only do one FAT in terms of the number of copies. With the updated code, they now allow you to specify, hey, I want you to create 2 FATs when you do this. So for various reasons, I wanted the latest. Now, with the latest, the one concern that you have is that if you go in that IDE and touch something and rebuild the configuration, it's going to wipe all these files out and put the ones that it wants in back. So you have to be aware of the fact that you got to manage these files somewhat outside of their preview. One final note about this kind of this core piece of this FAT file system. There's this file out there called ff.c and ff.h. And if you look in the ff.h, I added one function. So this exists only if the debug define is present, so it wouldn't be in production code for me. It would only be in development code. And basically what this is it runs a kind of a primitive check disk function that allows you to, if you have multiple FATs, you can compare the FATs, make sure the two FATs have identical content. You can walk the directory to make sure that everybody has a, well, what do I call, a finite length cluster chain that matches the file length itself. So if the file length is only 10 bytes and you got a cluster chain that is anything more than one cluster, there's something wrong. There should only be one cluster. So it's checking all that stuff to make sure everything's self-consistent. And then there's a option to print when you're doing that as well. So if you want to see, because it probably takes, I don't know, I got a 32 gig drive with not very many files on it, like maybe 100 or 200 files on it. And it probably takes, I don't know, a minute or two to complete one scan. So, and while it's doing that, it's locked access to the file system, so nobody else can be doing anything with it. So this is really appropriate for, like, you've used something all day long on a bench test or something, and at the end of the day before you go home, you might kick off this check disk operation to make sure that your file system's still intact and nothing has been corrupted. Hopefully you found this useful.